thank you again to all the speakers and giving us a really, a great overview of what their needs are. I think the big takeaway is having relevant and fit for purpose reference materials. This includes relevancy to the application area, whether it's emergency response or nuclear decommissioning and of nuclear power plants, long-term monitoring. Also fit for purpose with regard to sample size, which I know the FDA folks are interested in. Fit for purpose with regard to what actual isotopes or elements, radionuclides, are to be certified, things like that. What I think is one of the very important questions is obviously there is a lot of reference material needs, and also, sorry, I forgot to mention the age dating reference materials, which is also very important for many applications, including obviously climate, which is critical. So, but these are a lot of reference materials. There's not that many metrology institutes or designated institutes across the world, so it's hard to address everything. So I kind of would like, I think, to start maybe the conversation by hearing from what the metrologists are thinking with regard to what the stakeholder needs are and what they think is potentially feasible or not feasible, things like that. So I open it up to the floor. And of course, by the way, I forgot to mention, if there's any questions for the stakeholders specifically, then please do.
Well, I am noticing that NIST is on, the NRC in Canada is on, the PTB in Germany is on. So, Richard.
Yeah, I guess I could make one comment, and unfortunately, it's a resources issue. Recently the U.S. and sometimes with some international partners has been able to produce some very useful reference materials, protactinium calibration material, some very high purity plutonium-244 and 233 uranium spikes, and a thorium-229 material that was certified not for activity but for actual isotopics and amount. But that was essentially funded for a particular use because there was no reasonable expectation of cost recovery. And for many NMIs producing reference materials, that's a non-trivial thing, is that you've got to have enough of a customer base to sort of justify the investment of resources. And I think for many of the kinds of things we're talking about, that's a big hurdle. And maybe others have sort of similar comments or other perspectives on that.
And Richard does have a point. There's not a huge number of NMIs either across the world, so that makes it more of a challenge. Mike, you popped up, so I wasn't sure.
I'll add a little bit to that. I'm sorry, I missed most of what you said, Richard, but I heard the last end of it. But yeah, as an NMI and a CRM producer in the form of NIST SRMs, that type of practical consideration really drives the ship. Can we recover our costs? And so it's the extent of the customer base, but it's also something else that was referred to yesterday. It's the stability of the reference material. It's not stable enough to have a long enough shelf life, and that actually very much works against the anybody taking the reins to make it. So those practical issues cannot be overlooked. And I suspect it's pretty much the same story for most of the NMIs around the world.
So Dirk, did you have something?
Yes, maybe the PDB perspective from metrology part or side. So for reference material certification or characterization, I think we have already the capabilities for the field of radioactivity measurements, and we are currently building up these capabilities for mass spectrometry. That means the measurement side I see is growing at PDB, but what we definitely have not is the capabilities to produce a raw material. So everything what is requested on stability of the material and the pre-processing of the material, that is not in our hand. But if we, let's say, receive a raw material which has to be characterized and the radionuclides to be measured, that is what is within our field.
I think there's definitely been, within the U.S. working with, to some degree, the stakeholders or the customers to get, as you say, the raw material that, they can get that for us, and then we can do the characterization and development of the material, reference material for them. But yeah, that's very important because we have the same issues getting access to the raw material. Richard, I didn't know if you wanted to bring up the nuclear forensics reference material for the age or the model age. I thought that might be of interest for the low-level ICRM working group, just as an example of a material that people can use from. At least I don't know if the actual age range for that particular one is useful, but for that material, it's at least a good example.
So are you talking about the enriched uranium materials that we worked on?
Didn't you? No, I thought you did. There was a model age that you put together for one of the reference materials.
Yes, these are. There's actually two of them. One was a 63% enriched uranium oxide, and that's a U308, and a 4.5% enriched UO2 material.
Okay, sorry, that's
these are thorium-230, uranium-234 model ages. So those materials are out there. Actually, IRMM has a solution for the uranium-234, thorium-230 model age as well. I think there's some other projects. These are mostly associated with the needs of the International Atomic Energy Agency that are in the works for producing some synthetic aged reference materials for uranium.
Thanks. And also, I know maybe of interest as well as the British Geological Survey has folks there who've been putting together essentially reference materials for uranium lead. I know uranium lead, there's a couple other, I think uranium thorium, there's I think a few others they've been working on. So that's another group of people to contact. Zoltan, I see you have your hand up. Please go ahead.
So maybe I just speak for a little bit for NRC, and as a traditional chemical reference material maker, maybe a bit following up on Mike Winchester's take on practicalities and how the chemistry mindset or the chemistry reference material, mindset comes into reference materials for this radiogenic space. So we just recently completed a major effort with our nuclear regulatory agency of creating a suite of uranium ore concentrate reference materials, where basically step by step addressing the nuclear fuel cycle and regulatory and nuclear forensic needs on that. So this is a matrix reference material with ultra high uranium precision and isotope ratio precisions and full elemental fingerprinting coverage for these materials. And what we have quickly learned as a chemical reference material maker entering to this radio space, that although international collaborations and networks are useful to produce these materials, however, distribution and access to materials and access to expertise is quite limited. So for the chemist or the chemical folks on this call, regulatory considerations on who can access, where you can distribute are obviously way more stringent than for any chemical materials which we deal with. So embarking or starting programs, standards or reference materials program in this space, the practicalities of who are your customers and can access your materials should, which is, has impact on cost recoveries, should indeed be in the forefront of any planning activity. Thank you.
Thank you, Zoltan. I think NIST has been involved with at least selling radioactive reference materials for quite a long time, so I think we have a relatively good idea of how to do that. So and it works well. But yeah, I mean, we have to be careful about who is accessing those and who is purchasing them. So, but so I guess the question kind of lies in what is a path forward to help essentially address these needs that are needed by these stakeholders. I mean, what can be done? Where do we start? Oh, there's something just popped up in the chat. Hold on. Let's see, it's from Leslie Swift. It would be useful to have a central resource with advice on which type of measurements are possible with each particular type of mass spectrometer, and also some standard methods. This would help those who wish to begin using mass spectrometry decide which instruments to buy that meets their individual needs. Going forward, this could provide assurance along with the reference materials and PT schemes that our results are comparable. Apologies if this is available somewhere already. If it is, if someone could please provide a link. I think at least partial answer. I mean, I think a lot of the NMIs kind of do highlight their capabilities, but it's not necessarily in a centralized location that I can think of, unless somebody else is aware of that, and I don't know.
Well, Dirk turned on his video, so maybe he
he has his hand up. Go ahead.
Yes, that is exactly one of the planned outputs of the MetroBERM project, to really have such a guidance document on hand, comparing different measurement or mass spectrometry systems, and depending on what your question is or what you want to measure, that this guidance document should help you to select the right system, and in addition to have information about the possibilities how to calibrate the system. That should be one of the outputs.
Excellent. She says, perfect, thank you. So are there thoughts, whether it's from the stakeholder side or the metrology side, on how, how would we move forward again to address their needs, reference materials, or even proficiency testing needs? I know that at least within our division at NIST, there has been, I think, a considerable expansion, at least since I've been at NIST, in participating in proficiency testing type programs and adding those to, the program that we never really had as many before. I think if interested, I think Mike can probably talk a little bit more about some of those. They predominantly seem to lie within our organic group, but we have ones for food and we have ones for cannabis and things like that. So, but how do we move forward? Any thoughts?
I have one thought, and I don't think this is original by any means. I mean, the difficulty of producing complicated matrix reference materials is fairly daunting in some cases. Whether it's the very large amounts of material, tens to hundreds of kilograms, homogeneity issues. I mean, how people have talked about slurries or adding calibrated solutions, but is that appropriate when in the real world some of these radioisotopes might be fixed to particular compounds that are of interest? It seems that given resources, maybe something that NIST does a lot of, our radioactivity group, is produce sort of single element solutions that are very well characterized. And that might provide starting materials for other groups to produce some of these materials. I mean, I know that Wrestle essentially does very similar sorts of things, because I mean, just from what I've observed, some of these materials that a lot of these groups or agencies need, I think it's just beyond current capacity to produce them, certainly in the variety that's needed. I wonder if just focusing on sort of well-characterized starting materials in the radionuclide suites, some of these radionuclides that were mentioned that are not sort of traditional to the things we produce might be of interest.
I'd like to hear the stakeholders' thoughts on that. Does that seem something that would be helpful? Is there a different path we could take?
I can say a few words.
Yep, great. Go ahead, Lynn.
I think the comment just given is a very relevant ones, and I like what it says. When we talk about the reference material at the user levels, and we tend to believe if there is a single radionuclide standards, well characterized, and I can make my own cocktail from it. And then given I know the matrix I'm interested in, and like what the Wrestle is doing, right? And just spiking in-house some sort of standard materials for method development and validations, that will serve the purpose. The problem right now is I have two issues. One is the radioactivity standard is not same as a mass spectrometry standard. The reason I say that is, now if you look at the standard used for mass spectrometry measurement, every single isotope is actually being well characterized in terms of what is the atom percentage in there, right? But if you look at the radioactivity standard, they don't have that kind of information related to the mass spectrometry measurement. That's why the Wrestle is run into issues when they're mixing the cocktail together. And he said, you alter my original analyze, right? Because I have no ideas. I combine the 3 or 4 standards together, and my analyze is actually coming all over the place. So this is issues for users. Even we want to do an in-house reference material for a practical purpose, but without knowing the original primary standard well enough, it really lost all the traceability we are talking about here, right? So that's one thing I observed from our side of the operations. Another observation I have related to the matrix standard is this, right? I think on the national metrology lab level, you provide excellent instrument calibration standards, and which users use for either the spiking purpose or calibrated instrumentation for optimizations. Those standards are excellent. It's way beyond our expectations. So our problem is now is when we go down to the bench, get hands dirty, and all of a sudden the matrix issues in front of us, right? And we have not seen at the national metrology level can provide a complex matrix that really fits into our sample type. And I see some comments in the chat talk about the representative, right? And this, what they're really talking about is not only the representative of the sample in terms of a matrix, the chemical composition of it, and also the level of interference typically encountered when you measure the radionuclides. So these two things, in terms of a representative of the matrix, right? It is very challenging. But I thought, as a user, I can go out to buy any kind of food on the market I want, right? And if I realize this is going to be the typical interference that's going to be there, and typical chemical challenge to my sample digestions or chemical separations, And as long as I have a reasonably well-characterized primary standard and make a cocktail, spike it, I can do my job. So I agree with what Richard says. You know, I think as long as you can provide a whole host of a primary standard with a well-characterized property, I think you can count on the user and to make this magic reference material themselves.
So it sounds like having a reference material that's certified not only on a mass basis in the atom abundances, but also on an activity basis would be useful.
Yeah.
Because then if you first, you know, if you're mixing them and you know them really well, including the minor constituents guy, you know, you know what you're mixing and you know what you have, you know what you're dealing with. Okay.
Yeah.
So Guy, if you get DOE to buy us a multi-collector, I'll hook you up.
You got it.
Mike,
Are you willing to come to my lab and use it, Richard?
That might be a little difficult, especially when it's minus 20 C.
I'm not sure whose hand was up first, Mike or Begonia, but how about we start with Begonia? Go ahead.
Okay. I agree that a good primary solution could be very useful, but this is not for all the matrices. I mean, there are complex matrices where the radionuclides are in the mineralogical structure. So you are testing not only the measurement method, but also the preparation method. So there are some problems related to, as has been already mentioned in some of the presentations, related with the method used to get uranium, for example. No? So, of course, as I told, it's good to have these very good primary solutions, well characterized for mass spectrometry, also for radiometric, but it's not solve the whole problem, the whole issue. Okay? That's all.
Right. I agree. And there's also in the chat supporting what you're saying, the challenge there is to have a digestion method to ensure adequate extraction from the matrix and real samples. If not, you have the problem that Guy actually showed on some of his slides, where, you know, labs were reporting it 0 or they were biased in some way. So yes, that is true. So I think, you know, maybe a starting point is to have kind of these really great primary standards, but there are still matrix standards that are needed. Mike, go ahead, your hand is up.
That actually is a good introduction to what I was going to bring
Mike,
up.
it's hard to hear you. It's a little hard to hear you.
Okay, can you hear me better?
Yes. Yes.
Okay, I'll just lean in. Sorry, you're going to look at my nose, but that's okay. Yeah, so what I was going to say actually is the comment in the chat actually leads into it. And it is that, at least in the chemistry area, you know, when we make a matrix reference material, it's always better if the analyte we're actually trying to measure is there naturally rather than spiked. Because it's bound into the matrix in a different way than if it's just mixed in and spiked in. So I'm just wondering, for this community, how important is that consideration? Because I think what's been described in the last 10 minutes or so is taking well-characterized, by another term, you know, pure materials and spiking those into a matrix to make a matrix reference material. But it doesn't matter to this community whether that is, you know, naturally incurred or spiked in, and therefore it's easier to get out in an extraction if it's just spiked in than if it's actually naturally incurred.
Lynn, why don't we go to Lisa first, since she had her hand up, and then we'll hear from Lynn.
Great, thanks, Jackie. Can I share something?
Sure.
So I would just like to remind everyone about what the NMIs have in the radionuclide metrology side, what they have in terms of measurements of radioactivity in matrices. This screenshot that you're seeing here is from the Key Comparison Database, a listing of CMCs, calibration and measurement capabilities. Now, it is true that this is not telling you that this is from the NPL, that the NPL or the LGC from the United Kingdom, they may not have urine with uranium to sell you, but what this information does give you is the kind of measurement range of a specific radionuclide in a specific type of matrix that they can do. So to get to this particular page, I simply searched for material and uranium. So you can, and the Key Comparison Database is available to anyone. You go to the BIPM website and you can get to it. And you can get a very good idea as to the types of materials and the radionuclides which the NMIs and the designated institutes are doing. That's really all I wanted to contribute at this point, but thought you might like to remember that. Thank you.
Useful. Thank you. Lynn. Oh, sorry. Lynn, are you there? You have your hand up.
Okay.
Okay.
I just tried to unmute myself, and I think that a couple of comments before me is well taken. I think from the sample analysis perspective, the sample preparation is really critical. Many decades ago, and there's a debate between the natural matrix standard versus a spiked standard, right? That issues, I don't know, eventually settled or not, but I think two camps do have their own points that time. They all have their unique perspective, right? Of course, in the ideal world, the natural matrix standard definitely the best choice for developing the method, also for the validations, because it's naturally incorporated into the sample matrix that you are actually trying to analyze. It represents all kinds of challenges. We all know this, right? And but in reality, is this type of the matrix will contain the radionuclides you need to measure, or at the levels you prefer, and not even mention all other interferences embedded to have an impact on your measurement. It's very difficult to find it, you know. And I know NIST has a lot of natural matrix standards. The whole idea is driven NIST to have these kind of natural matrix standards is for that particular reason, because they truly believe this is the kind of material really truly representing the nature of the samples. And I think Russell also has a lot of opinions over the years and insist, you know, the natural matrix is the thing. And they even have this very passionable, I believe, the way of digesting the sample insists to say, if you don't total dissolution, right, your number never going to be right. And they demonstrate it, you know, and we've seen it. So as a user, I can have a choice like this. I can wait for another 20 years and retired. I don't see a single such reference material going to be there for me. Or I can take it back and look at my procedure and say, okay, at least if I can get my 30% of procedure, 50% of procedure validated, right, in some way, and I'd rather to have something than nothing. This is how I see this thing. So there is a practical things here we have to deal with, you know, and yeah, theoretical things is beautiful sometimes, but in reality, we just don't have the resources. We don't have the even opportunity to find the ideal samples we're looking for, not even mention how many communities are looking for different things. You guys are going to win the Nobel Prize if you provide a whole host of different reference material and make everybody happy. It's because that level of expertise and efforts, it just not even exist at this point. Thank you.
You're muted, Jackie. You're muted, Jackie.
Thank you, sorry. I was just gonna say, let's go to Guy, and then there's something from Marta in the chat. Go ahead, Guy.
So Lynn, thank you very much. You know, you answered your question, right? So if you could get the world to go to total digestions, you know, then everybody could spike their own materials and guarantee that they're going to get the right, well, pretty much get the right answer if they can go through total dissolution. But that's the problem, especially in the mass spec world, where, you know, leaching type of samples is pretty much king, right? And so laboratories don't want to use hydrofluoric acid. You know, they don't do microwave. Some of them do microwave digestions, but then their hands are tied because they can't use hydrofluoric acid because it's a safety concern or whatever, right? Molten salt fusions, of course, require, you know, usually platinum dishes. But then, you know, there's a lot of other techniques that have been easily been developed, like, you know, sodium hydroxide fusions in zirconium crucibles, right? So those methods have really come around in the last 10 years. And, you know, zirconium crucibles are only $50 a shot for, you know, a dish, right? Sodium hydroxide is very cheap. So if we can get the world to switch over to doing total dissolution, I think, you know, the world will be saved.
Thanks, Guy. So from Marta in the chat, she said, proficiency tests with participation of laboratories applying different digestion and analytical techniques may enrich the exercise when no matrix CRMs are available. That is a very valid point, to be able to maybe run an exercise to be able to prove capability that, you know, but you still need some kind of material that's somewhat like a, you know, CRM or RM to run that. But yeah, that's another way to approach it. I agree.
Lynn and then Begonia.
Okay, maybe there is another approach. Maybe I'm not saying anything new, but I understand that the development of reference materials in environmental or natural matrices is a huge task. But to have a list with the capabilities of the mass spectrometry reference laboratories would be nice in order to see, for example, if I need to check my technique in my university laboratory, I can send some sample, natural sample, to the lab in the list that is, let's say, able or capable to make the measurement by mass spectrometry.
So that almost is like sounds like a calibration. Like Lisa, maybe you can, you know, when we have all these calibration services, it's almost like an
it's
approach.
Like a calibration service.
Yeah.
Yes, like
yeah, almost like that.
I send my matrix.
Right.
Yes,
I want to check my results, and I can provide these results, this checking in my papers, for example.
Yes, that would be a calibration service. The current CMC's calibration and measurement capability claims on the key comparison database do not have mass spectrometry as a category, but we do know in CCRI section 2, we do know that there are laboratories that are using mass spectrometry in the analysis of their radionuclides. Part of the goal of this workshop was to see how we could do that better and expand that more. So that's a very good justification for actually trying to work this problem out even further. But as I said at the very beginning of the workshop, using mass spec in radionuclide metrology is really a very nascent, it's very early in its life cycle. And we're hoping that the information we're getting from all of the stakeholders and from each other, because we did have those good talks at the beginning of the workshop, will help grow this particular plant.
Lynn, your hand's up.
Oh, I just sent a quick question in the chat. I'm just wondering if there's any representative from NBL in the US in this workshop, because as I know, they host this whole mass spectrometry standards. Is that right?
I can, if nobody else is here, I can speak to that a little bit. I worked at NBL for a long time, and I'm currently collaborating with them on things. They handle mass spectrometry standards for uranium and plutonium, and also assay standards for uranium and plutonium. There's a couple other things that they're involved with too, but for the vast majority of radionuclides, the New Brunswick Lab or NBL program office now is not involved.
I see.
Thanks, Richard. There's a comment from Zoltan in the chat, and he says, perhaps for more in-depth conversation on CRMs for this community, dedicated sessions at the next edition of the BERM conference could be organized. The BERM is an international symposium on biological and environmental reference materials. This is an excellent practical forum for public and private CRM producers. It's a great idea.
So do we know when the next?
I don't know when the last one was.
Zoltan, maybe you know.
Yeah, do you know?
Angelique, are you on the call?
The last one was
Angelique Bota.
Yes.
So do you know the practicalities? Can you record the practicalities for the next BERM?
We were hoping to have the next BERM in next year, actually in 2024 in China, but it might be postponed for another year because we haven't really started on the technical program for the conference yet. So, but it is in discussion. Actually, the group of publicly funded reference material producers that meets quite regularly to discuss collaboration on projects is currently also discussing the logistics in terms of the next BERM conference. So we will keep you posted.
Be sure to include a session on the use of mass spectrometry and radioactivity measurement.
Yes, definitely. We also want to have a session on isotope ratio measurement, so it could possibly be a combined session.
Is that also going to, sorry, is that going to be a hybrid conference, or are you planning on making it a hybrid so that people can participate virtually, or no?
I think the current trend will be to have it, to have the possibility to hybrid the conference, but yeah, the focus is actually to get everybody together in person. But
ideally, yeah, but sometimes travel just is not easy.
Yes.
Thank you. Is there any other input from anyone? This has been I think, a fruitful discussion. It's quite quiet. Lisa, I don't know how long you had planned for that particular discussion section.
Well, I wanted it to go to its logical conclusions, so I think we may be there. Oh, sorry.
There is a hand up. Daniel, go ahead.
Yes, hello everybody. I'm Daniel from PTB. Can you hear me?
Yes. Yes.
Okay, because I'm testing these earplugs and I'm not sure if they were properly okay. I've been hearing the presentations of the stakeholders this morning. Well, this morning for me in Germany, and I have a question I would like to ask them all, if they can give it a global answer. As I got it, they kind of had their radiochemistry and radiometric established, and at some point they added on the possibility of including mass spectrometry measurements. I would like to know how much change in the previous phases of the analysis is included. So are they using the same structure, addition of tracer, radiochemistry, and measurement in exactly the same way they were using that, they were applying that for radiometric measurements, or did they have to, I don't know, change the tracers they were using, change some reagents, did some procedures turn out not to be useful for mass spectrometry measurements due to impurities or other aspects?
Mm-hmm.
Thank you.
Thank you. Guy, you popped up first. So, and then Guy first, then Simon.
Yes, yes and no. For the most part, the radiochemical procedures or methods are very similar, except at the last part, you no longer do a microprecipitation or a electrode deposition, right? You just end up taking the final fraction and diluting it to whatever you need to interject it into your mass spec. The tracers, you're absolutely correct. Like uranium, some people will change to using U-233 or U-236 for uranium measurements, right? Plutonium is still the same. A lot of people still use the plutonium-242. Americium-241 is used with the americium-243. That's still the same. What else? Thorium-229, of course, is the tracer for the normal thorium analysis. So pretty much everything has stayed the same.
Okay, so you didn't have to perform two separate validation schemes for the radiochemistry for the whole process.
Right. It's the same separation schemes, and then some things for uranium, of course, or like if you're talking plutonium-239, for example, you have to ensure you get the uranium out of the sample, or you might have the polyatomic, right? And so unfortunately, uranium's everywhere in our environment. So sometimes you have to do extra cleanup steps, right? To ensure that the uranium is almost totally removed. It's very hard to do, of course, right? But
yeah, it's very persistent.
You can get samples pretty clean, pretty pure.
Okay, thank you.
Thank you. Simon?
Yeah, Guy said a lot of it. Essentially, the procedures are pretty much the same. The tracers differ. For mass spec, we obviously don't use uranium-232, we use uranium-233. But as Guy is saying, the limit or the stringency of your purification changes considerably, because of the ubiquity of uranium, has just been said, but it also requires that the data that comes on your calibration certificate for your tracer, say plutonium-242 or uranium-233 or whatever, in radiometric terms, the certificates are fine, but if you're really driving down to extremely low levels by mass spectrometry, you really need better information on what's in the tracer, not For example, in a place I used to work at, we used to say there were no detectable impurities above 0.1%, which is perhaps great for radiometric measurements, but it doesn't necessarily work for mass spectrometric measurements. The other requirement is really, really, really knowing how good your blanks are. So at a superficial level, yeah, the game's the same, but when you dig down into the detail, you've got different requirements, shall we say.
Yeah, the blanks are very important.
That's what I was asking, Simon, to get the details.
Yeah, but I mean, in terms of how we do the analysis, stick the tracer in at the beginning every time. You know, I mean, it's sort of, I don't even think about it. You know,
and some of the reagents, right, Simon? So, we're switching over to using the ultra pure acids and, things like that as well. So.
Yeah, for sure. I mean, at NMBU, we spend quite a lot of time and effort producing large volumes of subboiled HF, HCl, nitric, I think phosphoric, et cetera, et cetera. To give an example of sort of blanks and backgrounds, we've been asked if we can look at iodine 129 analysis, and we've basically said we can't do it unless you build us a brand new laboratory unconnected to our current laboratories, because we know that small amounts of iodine 129 have been handled in the our lab area before, so therefore we can't stress here that it's not contaminated in a way that's a safety issue, but extremely low levels of iodine that may possibly be within the building means that we can't even think about doing iodine 129 work because of the mobility of it. So you have all these additional considerations which you have to think about.
Thanks, Simon. Lynn, you are next.
Yes, to answer the question of procedure, is it going to be the same or not? It is understandable for all the laboratory who is responsible for emergency response. And the philosophy is like this: they're going to use all equipment they have. So to be able to do this, they intended to have a one-size-fits-all kind of approach in terms of procedures. Because in the ideal situation, it'd be nice to process the sample at the end that you have different instrumentations that can measure it. So in that regard, the front-end chemistry has to be universal enough. That has been the driven philosophy for us. We try to developing any kind of sample digestions, radiochemical separation, and will allow at the end both mass spectrometry measurement and radiometric measurement, if we could. However, if you look at the two technologies, right, one is the emission energy based, another one is the mass charge ratio based. So in terms of a level of interference, it's not same. One can resolve one kind of problem, the other may resolve a different kind of problem. For example, aberration 241 measurement, right? And the two peaks is so close. So the resolution on the alpha spectrometry, you really need to make sure your source is massless. So attenuation is minimized so you can have a well-separated peak for 241, 243 for alpha spectrometry. But that's not the necessary requirement for ICP-MS measurement, right? Because you basically spray this solution into the ICP and you don't have attenuation issue. So you just based on the mass to charge ratio. So what does that mean to us? That means that the procedure can be simplified. you don't really need extensive radiochemistry, chemical separations, and to really remove the matrix to minimize the attenuations. You can relax a little bit for the ICP-MS in that regard, right? But if my manager talk to me and say, Lynn, I don't want you to run 2 separate procedures because it's too cumbersome. And what I do, I will do the one-size-fits-all kind of approach. So I try to let these things also can be measured by the alpha spectrometry, even though I know the ICP-MS don't really need this kind of degree of purifications.
Thank you, Lynn. And thank you for that question, Daniel. That was actually very interesting and a good question to ask. Richard, I'm going to cut you off because we need to move on, if that's okay.
Well, my point is very quick one, and that's another consideration is that the differences between counting methods in mass spectrometry, sometimes the difference can be in the amount of sample you need to get a measurement. So sometimes those can be dramatic given half-lives and amounts of material.
Thank you. So we're going to close this portion. And that was excellent discussion. I think it's going to get both sides thinking, stakeholders thinking about metrology and metrologists thinking about what stakeholders need. I think definitely have another meeting in the future would be great to kind of somewhat like prioritize what and how to go about targeting the needs. But thank you, everyone. I appreciate it. And again, thank you to our speakers.